Well, students, in this lecture, we will solve some problems from our chapter 1 on mathematical preliminaries. Let us take the first problem in the exercise of the chapter 1. The problem says that you have a real number L and a sequence of real numbers, sequence AN. This sequence AN satisfies a condition that says that modulus of an minus L is less than or equal to mu times modulus of an minus 1 minus L, and this condition is satisfied for all indices n such that n greater than or equal to capital N, where capital N is some positive integer, where this mu is some real number between 0 and 1. If this is so, then the question asks us to prove that an tends to L as n tends to infinity. The proof of this problem is interesting and also important because the technique we use in this proof is going to be used often in our course. Therefore, let us try to understand it and keep it in our mind. Let us try to understand the given condition more closely. We are given a real number L and the sequence AN is such that first finite number of terms in AN may not obey this condition. It may be that A1 is here, A2 is here, A3 becomes here, A4 may be here, A5 may come here, A6 may be somewhere very close here, and A7 may go here, and so on. So they may jump, but what is important is after some finite number of terms, say An, then you take any other term, say An, where n is something larger than capital N. Capital N can be included in this. Then the distance between this AN and L, that is this distance, is going to be less than the distance between AN minus 1 and L, that is this distance. And further you take the term AN minus 2, and the distance between AN minus 2 and L is going to be something more than the previous one, and it goes on like this till the term AN, that is capital N, right? So this is what is given to us. Now we have to prove that this sequence AN is going to converge. Remember, just the distance shrinking as you go on higher and higher in the terms of the sequence, it doesn't mean that the sequence is going to converge. There is a key condition given that this mu is sitting as a coefficient here, and that mu is less than 1. So this is very important, and this part of the condition is actually making the sequence to converge. Let us see how it helps us. What you do is you take your small n very large so that n minus 1, n minus 2 and so on all are greater than capital N. Now you apply the given condition to this small n that you have chosen. The condition obviously will hold for that n because small n is greater than capital N. Therefore, the distance will shrink like this, mu times mod AN minus 1 minus L. Now you look at this situation, n minus 1 is also greater than capital N. Therefore, you can apply the same given condition for AN minus 1 also. That is, replace n by n minus 1. That gives you, this is less than or equal to mu times mu into mod AN minus 2. You are applying the same condition by replacing n by n minus 1, right? That happens to be mu square mod AN minus 2 minus L, right? Now, n minus 2 is also greater than capital N. Therefore, AN minus 2 also obeys this condition. So apply the same condition by replacing n by n minus 2, and that gives you, this is less than or equal to mu cube into mod a n minus 3 minus l, right? Now you can keep on going like this. How far we can go? We can go up to a capital N, right? Because your condition holds up to here. After that, we don't know what happens. Okay. So up to a capital N minus L we can go. Now what is the power that comes here? Let us see, this would have gone some k times, right? So N minus k, something which is like this, has now become N, right? If that is so, then this should be your k, right? What is that k? K is nothing but n minus capital N, right? So you have mu n minus capital N times mod a n minus L. Therefore, your given condition can be written as a n minus L is less than or equal to mu to the power of n minus capital N into a n minus L. Now take n tending to infinity. Since we are given that mu is lying between 0 and 1, we can see that mu to the power of n minus capital N is a fixed number, right? So that is not a problem. This tends to 0 as n tends to infinity. Therefore, your a n minus L will tend to 0 as n tends to infinity. That is precisely what we meant by saying that a n tends to L as n tends to infinity. From here, you can also give a epsilon argument, but this is enough. You can directly conclude from here. Next, let us take the 9th problem. This is also an important problem in our course. We use this problem especially in deriving the error formulas for certain interpolation-based methods. The problem says that you have a continuous function on a closed interval AB, and we are given n points in the interval AB denoted by x1, x2, x3, x4 and so on till xn. They need not be equally spaced. And we are also given n real numbers denoted by g1, g2 and so on up to gn. Then we have to show that this relation holds for some xi in the closed interval AB. What is that relation? You evaluate f at these points, that is f of x1, f of x2 and so on, and multiply each of them by the corresponding real number that we have chosen and add them up. Now, there is a catchy point that if all these chosen numbers are of same sign, that is, everybody is either greater than or equal to 0 or everybody is less than or equal to 0. It's not that G3 is say minus 2 and G5 says 10. This kind of sign change will not happen. Either all GIs are positive or all GIs are negative. Then what happens is, out of all these Fs, you can just find a xi such that you can just pull this number f of xi out of your summation gi, right? So this is what it says. Instead of having the function value at each point xi, what you do is you just find a xi such that f of xi can be replaced by each of these numbers f of xi. That's what it says. You can find a suitable xi like this, and that xi is some unknown again. The xi is an unknown number belonging to the closed interval AB. How to prove this? Well, it is a very simple application of the intermediate value theorem. You look at this, f is a continuous function. That is what is the key here. We'll prove the result by assuming that all gi's are positive. The proof for the other case, that is all gi's are negative, can be done in a very similar way. So we will write without loss of generality. We assume that all gi's are positive. Now you see, we have another set of real numbers, f of x1 to f of xn. Remember, they need not be of same sign. They may vary in their sign. Now what you do is you take the maximum of all these numbers and call it as f of x star. And similarly, you take the minimum of all these numbers and call it as f of x suffix star. Now you define a new function g of x as f of x into I is equal to 1 to n gi. Now, since it is given that f is continuous, you can see that g is a continuous function, and moreover, we can see that g of x superstar is equal to f of x superstar into summation I equal to 1 to n gi. Now you see, this is a fixed number, therefore you can push it inside the sum I equal to 1 to n f of x star into gi. And since x star is the point at which the maximum is attained, you can see that this number is greater than all the numbers f of xi's. Therefore, you just replace f of x star by f of xi's, and thereby you will get a greater than or equal to sign, right? F of xi into gi. Remember, all these gi's are positive. That is why you get the greater than or equal to sign. This is where we are using the condition that all gi's are of same sign. In particular, we have taken these gi's to be positive. Otherwise, the inequality would have been reversed. So when you take gi's to be negative, you have to just put the reverse inequality. And now you see x suffix star is the point at which the minimum is attained. Therefore, all these f of xi's will be greater than or equal to f of x suffix star, right? Therefore, you can write it as greater than or equal to sigma I equal to 1 to n f of x suffix star into gi. Now you pull it out of the sum because it's a fixed number, and you get I equal to 1 to n gi, right? And that is precisely your capital G of x star. Therefore, what we got is capital G of x suffix star is less than or equal to capital G of x superscript star. And not only that, we also see from the above calculation that the term which we want, that is this term, is going to sit between these two numbers, right? That is G of x suffix star is less than or equal to sigma I equal to 1 to n f of xi gi is less than or equal to g of x superstar, right? And remember, g is a continuous function. Now we are ready to apply the intermediate value theorem, right? I hope now you can apply the intermediate value theorem to get the desired result. I leave it to you to complete this problem now. Let us take up the 19th problem. Let me do few of them. Let's take the third question. We want to prove that or disprove n plus 1 by n square is big O of 1 by n. You can see that n plus 1 by n square is one sequence and another one is 1 by n, right? So you just take this as an and you take this as bn, and now we have to see that an by bn whether this sequence is bounded or not. So how will you write this? This is n plus 1 divided by n square divided by 1 by n, which will give you n plus 1 by n. Now that can be written as 1 plus 1 by n. In fact, from here itself we can see that both the terms goes with equal speed to infinity, right? So therefore n plus 1 by n square is big O of 1 by n. Okay, so this you can see that this tends to 1. So this sequence is bounded, right? This is bounded and in fact it goes to 1. So this is correct actually. You can also verify whether this sequence n plus 1 by n square is a small o of 1 by n. Well, that may not be true. I'll leave it to you to check that. But if you want to cross check the same sequences rigorously with the definition that is given in the class, how to do that, let us see. You have to show that an is less than or equal to some constant times bn, right? That is what we have to show. This should happen at least after some finite number of terms. It may not happen for all terms, but you just discard some finite number of terms. Later onwards, it should happen. That's what we are demanding. But again, this is very easy. You can check this. An is n plus 1 by n square, and that is equal to 1 by n plus 1 by n square. So you just take 1 by n outside, 1 plus 1 by n, and 1 by n is less than or equal to 1, right? So that you can use here, 1 by n into 1 plus 1. See, this bn is nothing but 1 by n, right? So somehow you have to retain 1 by n here and make this somehow a constant, right? That is why I am replacing this term by 1, but retaining this term as it is, okay? And that gives me 2 times 1 by n. So my constant c is actually 2 here. If I go with this kind of idea, then it is 2. And that tells me that n plus 1 by n square is actually big O of 1 by n. Okay, let us take the fifth problem and see what is happening with that. We will see both intuitively and also check the definition. From the examination point of view, if I ask you such questions, I will expect you to check the definition and show, not the intuitive arguments. So let's first take the intuitive argument, 1 by log n. The intuitive idea is just to be clear about what is happening with these sequences. But when you go to prove certain things, you have to give a rigorous mathematical justification, although they may be intuitively trivial. So let's do intuitively that you take this as an and this as bn, 1 by n. Okay, then an divided by bn is what we are doing, that is n by log n, and you can see that this goes to infinity, right? As n tends to infinity, that itself shows that 1 by log n is actually not small o of 1 by n. Okay, that's intuitively clear. Let's try to prove it rigorously by cross-checking the definition. Remember, we have to show that for every epsilon greater than 0, there exists a n such that, of course positive, an should be less than or equal to epsilon times bn. What is an? An is 1 by log n. And what is bn? Bn is 1 by n. Assume it holds. See, if you see intuitively that something is true, then try to directly prove it. If you see intuitively something is not true, then try to prove it by contradiction. So here we saw intuitively that this is not true. Therefore, we will try to prove or check the definition by going in a contradicting way. Assume that an, that is 1 by log n, is small o of bn. Okay. Then what happens is, for every epsilon greater than 0, I can find a n such that 1 by log n is less than or equal to epsilon into 1 by n. Well, I need not put modulus, for all n greater than or equal to capital N. So if I assume that this is 1 by log n is small o of 1 by n, then this should happen. That means what? N should be less than or equal to epsilon times log n, right? Now, if that holds, then n by log n should be less than or equal to epsilon. Now you see, this is a sequence which tends to infinity as n tends to infinity, whereas this is a fixed number. You will always see that if the sequence an is not small o of another sequence bn, then you will always arrive at such contradiction. That is, the left hand side will be growing drastically, and that will happen to be less than or equal to a small number. Okay, such things will happen, and that will tell you that this assumption is wrong, right? So this is a contradiction. Thus 1 by log n is not small o of 1 by n. Okay. So from the examination point of view, you have to check the definition and show us. Just the intuitive idea is not allowed. If you just write the intuitive idea, that is this one, I will not give any mark. You just have to give such mathematical argument going and checking the definition. You see, in that you anyway use this intuitive argument, right? But just to check whether you have understood the definition well, I would like you to prove it using the definition